All right, welcome once again to another episode of MATLAB and Simulink Accelerator course. So, what essentially we are talking about converting the solar panel hardware, which essentially is a panel with all sorts of diodes and has emitting of light that it receives to convert into electrical energy. And we'll be converting that into a Simulink model. So, that's essentially the topic of today. So, without further ado, let's recap of where we were. So, where we left last, and you can go back to that episode, we had done the cyclic daily solar measurement modeling, whereby we were able to synthesize from a cyclic or sinusoidal wave and do some state logic implementation for that to result in a irradiance value, which irradiance is essentially the intensity of light that was able to give us an input into the solar panel, and how the solar panel then uses that to convert that to electrical energy. And that is where we're going to be kicking off. Now, before we do that, it's quite important to take a bit of background on all these specific aspects. So I wanted to do a bit of literature just to get some clarity on solar panels. So there is there is some expectation regarding solar panels and what they're able to achieve. Now, the one thing that solar panels tells us, and we can go into that, is they have a specific efficiency, and we spoke about that a couple of episodes or episodes ago. That tells us, and or we should take into account when we are looking to solar panels. And the most important part is that there is a certain power from irradiance that gets received from the sun, but the inefficiency or the lack of efficiency of the solar panel only allows us to harvest up to 20%, and oftentimes on average 13% of that power. And essentially that is what you get. You cannot do anything more about that, potentially with different type of materials, and that should be taken account into your budget. But why is that? And that's essentially what we're going to be talking about today in part. And more importantly, when we talk about a solar panel, we talk about its current and voltage curve. Now, it gets into a bit in depth here, but the only thing that I wanted to mention very briefly is that the solar panel, like I mentioned in the intro, gives a sense that there is a light generating current, and then there's a diode that allows us to harvest that light generation current through having a potential energy between positive and negative, and that gives us the voltage. And with that voltage, of course, we are able to then charge a battery, for example. So there is a specific equation that allows us to look at the relationship between current and voltage for a light generating current diode, and that gives us an indication of how we are turning the light emission or the irradiance that we are getting hitting the solar panel and the diode, and with that essentially giving us the current that we need to charge our battery. Now, that's essentially what this is. This is essentially a very simple mechanism for harvesting light and generating a current for through a diode allows us to have a voltage, and with that voltage compared to a battery or attached to a battery allows us to charge the battery and then carry on from there onwards. Okay, so I think then what we are talking about is how can we translate all this into Simulink? Why is it so important to then at least evaluate what Simulink is able to do with respect to this? So we will go into directly into the model, and then I'll go through the various steps. So in this case, I will not model everything from scratch, but we will go through it directly. Right. Now, if you were to take a step back, a solar panel is can be modeled into what we call a subsystem. A subsystem in Simulink allows us to pack all the information that we need and only for the sake of simplicity worry about the inputs to the subsystem and the outputs of that system. In this case, the solar panel is seen as a subsystem, an object in itself, and the battery acts as another subsystem with its specific dynamics included. So the aim of this is to arrive at a point where you know exactly what the battery will be getting based on the solar panel and its irradiance. So let's try and go into the solar panel in this case. What does that help us to do? Now, a lot of these blocks we've gone through them before and some we haven't. And this is probably the most important part. When we look at the equation here and we try to understand what will that give us, we see that the total current coming out of a solar panel diode is a function of V is velocity, T is temperature, and then L is essentially the emitted current, for which in the case of 0 volt, that would be the value. And it can be written in another way where in the event that you have 0 volt attached, i.e. a short circuit, you will get the maximum current that that diode can give you. And of course, we know that as soon as you have current flowing, there is a voltage drop due to resistance. And then, of course, the current that you get at the end is lower than the ideal current without voltage. But for you to get to that equation, there is a sense that the model needs to incorporate all those values, right? So when we're talking about the specific value of trying to get to the current coming out of PV stands for photovoltaic, which essentially is the technical term for solar cell. And now, for us to model this, there's a couple of things we need to think about. One, we need to think about all the different constants that make up the equation, right? In this case, we have quite a few, right? So Q, we have N, we have K, I0, which just stands for the saturation current, and all of that have a specific value for a specific solar cell. Now, in Simulink, what you can do is model all of these as constants, mainly because they don't actually change. They are specific to that hardware, and it will not actually change. Now, secondly, what you can also do for you to be able to evaluate what this is trying to do is you can also ensure that it's modeled not as an equation, but as lines and block connected to each other. The main reason you do that is because Simulink will allow you, when you simulate, to interrogate every single line that is connected while the data is being passed. This is critical for troubleshooting, unlike a MATLAB script, because this gives you a complete control of every time step to directly identify where potential problems are. And we will go through that. Now, the next thing that is quite important is a solar panel is connected to a battery, right? A battery is a lot simpler to model in this case than a solar panel. Of course, an actual battery is a lot more complex than what I've done here. But the current and voltage relationship for a battery can be modeled very simply, which is you have a specific current that comes from the solar panel, and based on if there is a load, in this case the load, which means could be a motor, could be a light, could be whatever the case may be, would now, given the charge and the capacity of the battery, capacitance, sorry, of the battery, and a certain efficiency, will allow you to now work out the state of charge, which essentially means just how full or empty a battery is, and also will allow you to directly, depending on the rated or what we call open open charge voltage, which essentially is the voltage without no load, allows you to now work out what the actual battery voltage is in the event that there is current. That is essentially what this does. Now, what you can do with this is directly implicate the solar panel charge to a specific voltage and state of charge, which means and charging rate or percentage of fullness of a battery. So why is this important? Because without the solar panel giving you a charge, you will not be able to integrate or i.e. increase. And this is an integrator. The integrator is simply a way of just doing a for loop or just adding onto itself the previous value that comes into the integrator. So it will consistently add onto that value and hold it every single time we play. That's essentially what this does. So that's as simple as that. So the battery gives an indication of how the state of charge will work. Now, if you go back to the solar panel, the one thing that you will see is that there are inputs all over, right? So this is what we call an input, and this is what we call an output. Inputs are essentially mapped directly to what we see here, right? Irradiance is the same input that we see inside here. And that gives us an indication of how I'm able to connect and where the connections actually are routed to. And this is essentially all you need to know about a subsystem in Simulink, but the internals is what's more important. So the next step is to understand how do I then simulate all this? I've translated this equation from this essentially with a little bit more of understanding where the V here, if you remember your, I think which course was this? I guess electricity one, I don't know, second year is V is equal to IR. So you essentially can model V as a combination of current, which in this case is the current that is calculated, and the resistance inside the diode or the solar panel, and then that is voltage here. Now, if you think about this, there is a problem, right? The current that you want to compute is a function of the current that is required to compute it. We call that an algebraic loop. It can be solved in different ways. Simulink is very good at trying to solve an algebraic loop. And the one thing that we do in Simulink is we add what we call a delay. A delay is essentially saying at the start of the simulation, I need some initial condition. And in this case, this delay would initialize, and if I were to open it, you will see it will initialize with a condition of 0, which means when we pass through from left to right, i.e., because that's essentially how Simulink works, right? So every input goes from left to right and computes. We will start with the initial output, which gets routed into the input here at 0. So everything will be calculated at 0, and essentially only the value after will now be non-zero based on the calculation. That's how you're able to numerically ensure that there isn't an infinity loop that does not allow you to solve the model. Okay, so that is one more point. And the final thing that can give us an indication of on why Simulink also is a very powerful tool for modeling these type of nonlinear equations is you can have open inputs in the event that you want to use them for whatever reason. So in this case, I wasn't sure whether the voltage should be of any consequence. In this case, I put it to a specific value. I also wasn't sure whether the ideal diode should be a specific number. I put it a specific value, and we will see what it gives us. Okay, now finally, in terms of overall modeling, the one thing that Simulink is very good at is we can step through this model as for the first time we are simulating it, we can step through it on a step-by-step basis. So instead of pressing run, I can do a step forward. So if I were to press step forward, what will happen is it will step, and then what I can now do, which is incredible, I can now interrogate almost every single value by just every single signal by just clicking on it and seeing where is the data to the output coming from, right? So maybe I'm interested in knowing what's happening here. Interested in knowing what's happening maybe here, I guess, and I guess here maybe. So this is very different from a scope, which causes your model to look a bit untidy and you don't actually want a scope. This allows you to numerically interrogate the signals as you are simulating or stepping forward, right? If I were to do the whole run, you will not see the numbers change or how they change, but a step forward will allow you to see directly how these numbers would change on a step-by-step basis. So, for example, when I do something like this, I can see, okay, everything looks good. I get my short circuit current, which again, for a reminder, is the maximum current this solar cell can give me in the event of zero voltage. Of course, that's ideal, right? There's no such thing as current with 0 volt. And then it allows me to then work out what that specific current should be. Now I can immediately see that this actually doesn't look right, right? There's there is no such thing as a negative current to the power of 8. All of a sudden, because I've done this, I don't have to simulate and open up a scope and all of that. All of a sudden, I'm able to directly interrogate that this doesn't look right. So maybe another way of doing this is to basically say, okay, let me stop and then let me make this as 0 and see if that would make any difference. So I'll make it 0 and then directly we can redo the step forward. And then as we go through, we say, okay. So then I see that, yeah, this path gave me a problem, which means it potentially is incorrect. And more importantly, for a very small voltage, and we will go to what this is supposed to be, the irradiance all of a sudden, as we change the day, for example, as the day changes, makes more sense, right? So we are able to see changes as I go through and step through all the changes that make a bit more sense to me, where the fundamental current uh, based on the sun intensity is on this path, and then the voltage drop that also causes a loss in current due to the diode is on this path. And all of a sudden, I can see, okay, for really small sun intensity, I'm expecting this path to be really small, which means I'm very close to having an ideal current, but at the same time, I also know that I'm also having very small current due to the very small irradiance. So everything seems to be working out fine. Now, if I were to also get out of this and go in here, I will see exactly the same thing. So I don't have to change anything. I just have to put the voltage here and see what happens and just carry on, right? So I'm able to directly carry on and see what is happening. I see my status charge is now 18%. And I'm also able to see that I'm getting all the values that I need. In this case, I'm getting not used for whatever reason. That's quite interesting. And but the one thing that just wanted to show is just how the state of charge is changing as the current is non-zero, right? One definitely can see that. The current is non-zero, and of course, with that, one is able to directly see the state of charge changing. Okay, so what is that, as a summary, what does that tell us? It tells us that not only are we able to model directly a very complex nonlinear with algebraic loop in Simulink, but the solar panel dynamics is directly dependent on the output for it to work. That is fundamental in understanding how a dynamic model works, and more importantly, the inputs that are required to give the very values that will be needed, specifically in this case, to charge a battery. That's it for now. I just thought I should give you this overview. Hopefully, this was very useful. Next, we will go into how the battery connects to a very simple motor, and how we are able to go from these very simple irradiance, which essentially this is a repeating sequence, which is very similar to what we did before, but in a very simplistic way. And all of that will be connected to see how not only will the motor be working, but also how the battery will be charging.